So I'm going to talk about PCAN, which stands for Parallel Efficient Clustering with Graph-Based Approximate Nearest Neighbor Search. This is joint work with Shangdi Yu, Josh Engels, and Yihao Huang, all from MIT. This work appeared in ACDA just this past summer, so it's pretty recent work. So this talk is concerned with the problem of clustering. The goal of clustering is to group similar objects together and separate dissimilar objects into different groups. You can do clustering on both graph data as well as spatial data or point data. So in this talk, we're going to be focusing on spatial clustering. So we're going to assume that our data comes in the form of points or vectors. There are many applications of clustering. For example, it's used in financial applications, image recognition, information retrieval, and so on. We're going to be looking at a particular kind of clustering called density peaks clustering, or DPC for short. This was introduced by Rodriguez and Lau in 2014. It's gotten a lot of attention. It's a pretty popular type of clustering algorithm that is used in practice. This kind of clustering defines clusters as dense regions of points in your coordinate space. And it's able to discover clusters of arbitrary shapes. In contrast, something like k-means, which is also pretty popular, can only recover clusters with spherical shapes. So this is one advantage of DPC. So as an example, if we have this data set, which is a smiley face, two eyes and a mouth on the left, if you use k-means, you're not going to be able to find the three clusters. But if you use DPC, you can actually recover the three clusters corresponding to each of the two eyes in the mouth. And due to the advantages of DPC, it's been used in many applications. So this picture was taken from a paper published in Nature Medicine where they're identifying clusters of T cells, which are used in cancer studies. One limitation is that existing DPC algorithms are either sequential and therefore cannot scale to very large data sets, or they're specialized for low-dimensional data. So they don't work well for high-dimensional data. But in many real-world applications, we want to actually deal with high-dimensional data. So we need to have a solution that can scale to large data sets that are also high-dimensional. And this is the challenge that our work is addressing. So the contributions of our work. First, we unified the different variants of DPC out there into a single framework. There are many different variants of DPC out there based on variations of specific details that I'll talk about shortly. But our PCAN framework is able to unify all of these different variants by abstracting out several key steps that are common to this class of algorithms. Our framework is also parallel. So one of the key steps in DPC is to find nearest neighbors with a higher density. I'll talk about what density means later, but it's basically a restricted form of nearest neighbor search. And in PCAN, we introduce a parallel doubling search method that is able to do this pretty efficiently. And then finally, we have comprehensive experiments where we're comparing different variants of DPC under the same framework, and then we also compare to state-of-the-art solutions for DPC on large high-dimensional data. So here's an overview of the rest of the talk. So first, I'll define the density peaks clustering problem, and then I'll talk about some existing solutions, and then I'll talk about our PCAN framework, and then finally, I'll conclude with some experimental results. Okay, so DPC consists of three key steps at a high level. The first step is for every point in your data set, you want to compute a density for it. This density is just based on the density around the local neighborhood of the point. In this particular image, the density is computed by drawing a fixed-sized ball around each point and then counting the number of points inside that ball. That's one way to compute the density. But you can also imagine other ways to compute the density, and different variants of DPC introduce different functions for computing this. The second key step is finding dependent points. So the dependent point of a point is defined to be the nearest neighbor of that point with a higher density than it. So it's not just the nearest neighbor. It has to be the nearest neighbor with a higher density. So it's a constrained form of nearest neighbor search. Okay, and then in the second step, every point is going to draw an edge to its dependent point. So you're going to end up with a graph. In the third step, we're going to remove all of the edges that are greater than some distance. This threshold is user defined. And then what remains is a bunch of connected components, and each of these components corresponds to a separate cluster. Yeah, question?
The dependent point is the point of highest density that's in your circle, or?
It doesn't have to be in your circle. So everyone's going to compute a density, so everyone's going to have some number. And then in the second step, you want to find the nearest neighbor that has a higher number than you. So it doesn't have to be in your circle there.
So if you had a uniform space, then everyone would have the same density, and then this would do nothing, right? Or is
so I mean, I guess that wouldn't be a very interesting data set to cluster. So yeah,
right.
Yeah, but
easily amused, you know?
Yeah, but I mean. Yeah, I mean, just like in general, like everyone's going to have a different density. We're working with like floating point numbers, so you can assume every point has a different density. Yeah. Okay, so the third step, we're going to basically identify the connected components, and each of these components corresponds to a separate cluster. We also have these noise points, which are just outliers in our data set. So noise points are defined to be points that have a density lower than some threshold rho min. And then we're just going to remove these points from consideration when we're doing clustering. These are considered outliers because they're just too far from any other points in the data set. Okay, so existing variants and solutions for DPC. So the original DPC paper by Rodriguez and Lau, they defined the density to be the number of points within a fixed radius, which is what I drew on the previous slide. But unfortunately, this density measure doesn't work very well for high dimensional data due to the curse of dimensionality. So in high dimensions, like a lot of the distances are very close to each other. So using this kind of density measure doesn't allow you to differentiate between different points that have a different amount of importance in the data set. But the original paper was focused on low-dimensional data sets. A couple of years later, Flores et al., they introduced this SDDP algorithm, which uses a different density function. So they use the inverse distance to the kth nearest neighbor as the density measure. So you find the kth nearest neighbor, and then you take 1 divided by the distance to that neighbor, and that's your density. They show in their paper that this measure is much less vulnerable to the curse of dimensionality when working with high-dimensional data. And then a year later, Cyrano Gianfranti introduced the FastDP algorithm. So they use the inverse of the average distance to all k nearest neighbors as the density function. And then they have a pretty efficient implementation. It's a sequential implementation, but it's pretty efficient. It relies on using approximate k nearest neighbor graphs to speed things up. And a couple of years ago, my co-authors and I worked on a parallel DPC algorithm. But this algorithm was optimized for low-dimensional data. So it relied on a variant of a KD tree, which doesn't work very well in terms of efficiency when you're looking at high-dimensional data sets. There are a lot of other papers on DPC out there. Most of them are focusing on looking at different density functions and showing that particular functions work pretty well for certain applications. There have also been a couple papers on parallelizing DPC, but they're all for low-dimensional data sets, and there doesn't exist any solution that does parallel DPC for high-dimensional data. So we introduced the PCAN framework for addressing this challenge. So in PCAN, we make sure that all of the steps in DPC are parallel and scalable. PCAN is also able to include many different variations of DPC. So we include different variations of DPC density functions that are based on k nearest neighbors. And before I go into the specific components of our framework, I just want to show this slide again. So just to remind you, these are the 3 key steps of DPC. The first step is every point wants to compute a density. This density is going to be based on the local neighborhood of that point, but you can basically use different density functions here. The second step is every point is going to want to find its dependent point, which is defined to be the nearest neighbor with a higher density than the point itself. And then that's going to form a graph where every point is going to point to its dependent point. In the third step, we're going to remove all of the edges that are too long. And then we're also going to remove the noise points, which have a density lower than some threshold. And then we'll find the connected components in the remaining graph, and those are going to be the clusters. OK, so in our framework, the first step is we're going to construct some index. And this index is a data structure that can be used to efficiently find nearest neighbors. So this could be something like a KD tree if you're working with low-dimensional data. If you're working with high-dimensional data, you can use something like a graph-based approximate nearest neighbor search index, which has been quite popular in practice. We're going to use this index to compute the k nearest neighbors of every point. Using the k nearest neighbors, we can now compute the density of every point. The fourth step is to find the dependent points of every point. So for this, we're going to need to use the densities that we computed, but we also are going to need to look at our nearest neighbor index. That's going to help us find the dependent point. One optimization is that maybe our dependent point is already in our k nearest neighbors. So we can just do a brute force search over the k nearest neighbors that we already retrieved previously, and then see if there's one that has a higher density than us. And if so, then we'll just pick the closest one to us as the dependent point. OK, next up, we're going to find the noise points. These are the outlier points. And then finally, we'll compute the clusters after we get rid of the noise points. So for finding the noise points, it's a simple application of a parallel filtering algorithm. For computing the clusters, we're going to be using a concurrent union find data structure. OK, so as I said earlier, the index that is in our framework, it just needs to be able to support finding k nearest neighbors efficiently. These can be exact k nearest neighbors or approximate. So in high dimensions, we're going to work with approximate nearest neighbors, and therefore the clustering we get is going to be an approximation of the true clustering from DPC. We also require that the index have a parallel construction routine because we want to make sure all steps of the framework are highly parallel. So I already mentioned this. So for low dimensions, you can use a KD tree. For high dimensions, you can use something like a graph-based index. And there are many efficient parallel implementations of these two classes of indices out there. OK, so let's now talk about finding the dependent points. So how can we use a regular nearest neighbor index to find the nearest neighbors with a higher density than the point in question? So there have been previous solutions for doing filtered nearest neighbor search. However, all of these previous solutions assume that each point only has like a categorical label on them, and there are only very few of these labels. So they assume a small number of categories. But in our scenario, every point could have a different density, and therefore every point would belong to a different category, and these existing solutions would not scale to this setting. So what we do is we use a doubling method, which I'll talk more about on the next slide. But this approach supports numerical filtering criteria, where we can say, for example, give us the nearest neighbor of this point that has density greater than 0.5. And this method is generalizable to any index that can support regular nearest neighbor search. So the doubling approach, it's pretty simple. So the remaining points are the points that still need to find a dependent point. So for each remaining point we have, we're going to find the k nearest neighbors for each of these points. And then within these k nearest neighbors that we find, we're going to try to find a dependent point within the result. And we're going to do this by first using a parallel filter to see if any of these points have a higher density than us. And if there are at least one such point that satisfies this criteria, then we'll do a parallel min to take the closest one. So some of the points will find a dependent point in this round. Some of them will not. And then we just double k, and we do this again until everybody finds a dependent point. So in the worst case, you're going to only need order log n rounds because you're doubling the number of nearest neighbors you're finding. So after log n rounds, you're going to be looking at the entire data set. In practice, we're not actually going to run this until every point is looking at the whole data set. So We found that in practice, switching to a brute force search when there are few points remaining is actually more practical, because at that point it's actually just faster to do a brute force search instead of continuing this doubling process. Okay, and then for the third step, which is computing the clusters, so recall that we have a graph after we find the dependent points, where each point has an edge pointing to its dependent point here. And here I've also labeled the edge with its distance. And now let's say my threshold is 1.5. So I'm not going to consider any edges with a weight greater than 1.5. So I'm just going to remove those, and then the connected components are my clusters. And then to actually implement this, we used the parallel union-find data structure by Jayanti and Tarjan. So what we do here is basically every edge that has a weight less than 1.5 is going to call a union. And these union calls can all be done in parallel. So here we're going to call union on the edge from F to A, from B to C, and then the edge from C to D. And then we're going to skip the edge from E to A and the edge from A to C, because those are too heavy. And then after we're done with that, everybody is going to call a find in the union find data structure, and then the result of the find is going to be the cluster ID. So as an example here, the find of A and the find of F give you the ID A, so they belong to cluster A here. Okay, so that's a pretty simple application of union find. Let me now talk about some experimental results. Okay, so we implemented the pecan framework using C++, and we use a bunch of parallel primitives from Parallelism by Blalock et al. For example, we use the parallel filter and the parallel minimum from that library. And then for the nearest neighbor search indices, we use the graph-based indices from Parley ANN by Manohar et al. For most of the experiments, we use one of the indices known as Vamana, but we also have an experiment showing that different graph-based indices from Parley ANN perform pretty similarly. Most of the experiments use the density function defined to be the inverse to the kth nearest neighbor, where k is set to be 16. So we found that this works pretty well in terms of getting good quality clusters at a reasonable running time. But I'm also going to be comparing the different density functions that we tried in this section. And we ran our experiments on a 2-socket machine with a total of 30 cores. We tested on both synthetic as well as real-world data sets. For the synthetic data sets, we created data sets with sizes ranging from 10 to the 5 to 10 to the 8. The number of dimensions was 128. And then how we constructed these data sets was we first selected the number of clusters we wanted, and then we distributed those randomly in this 128-dimensional space. And then for the remaining points, we divided them evenly across these clusters. And then we generated the clusters just using a Gaussian distribution with a fixed mean and variance, where the mean is basically where the center point is for that cluster. We also tested on some real-world data sets, including image as well as text embeddings. The sizes of the data sets range from 70K to 1.28 million. Dimensionalities go up to 1024. And then the number of clusters varies from 10 to 1,000, depending on the data set. Okay, so first we looked at the performance of these different density functions. First of all, the y-axis here is ARI, which is a measure of cluster quality. So higher ARI corresponds to better clustering quality. And then the x-axis here is the clustering time in terms of seconds. The kth here, this kth function is basically the inverse to the kth, inverse of the distance to the kth nearest neighbor that I talked about earlier. And then there are also these other functions. I'm not going to define them here. I do have a slide that defines them if you want to ask me later. But they're basically different density functions that were proposed in the literature, and we also tested those density functions. And then the number on each of these data points corresponds to the value of k that we use. So for example, 16 corresponds to using 16 nearest neighbors. Okay, so what we see here is that the kth function, using the inverse distance to kth nearest neighbor, performs the best in terms of quality among all 5 of these functions here. And it's also able to get these high quality clusters at a pretty similar running time compared to these other functions here. Another question we were interested in asking was whether using a larger value of k is better. And we see that it's not necessarily better. So we found that using a modest value of k, like k equals 16 or 8, actually gave us pretty good clusters already. And then using a larger value of k doesn't necessarily improve the ARI. In Reddit, it does, but for this burst data set, it doesn't. But it does increase the running time because now you have to search for more nearest neighbors, and that takes more time. Yeah, question?
Is it weird that like on the middle one, the lower numbers are higher, or is there just like in terms of quality?
The lower numbers.
Like the X8 is better than the X64 in terms of quality.
Yeah, I mean, I'm not too sure why that is the case. I mean, I guess maybe the further neighbors just introduced more noise here. Yeah, it's a good question. Other questions? All right, cool. So here we also tested the performance of the 3 different graph-based indices that we used in Parlay ANN. And here we're plotting the Pareto frontier of these 3 graph indices. So for each graph index, we can tune different parameters inside the index as well as inside the DPC algorithm itself. And this will give us many different data points in this ARI versus clustering time space. And then we just take the points that are Pareto optimal. So we take the points, we keep the points if they dominate all other points with a fixed ARI, but they have better clustering time, or vice versa. Yeah, question?
Am I reading this correctly, that HCNNG is actually a great solution according to this plot?
So for this particular data set, it's pretty good, but this isn't necessarily true across the board. Across all of our experiments, we found that they all perform pretty similarly. But yeah, for this particular data set, HCNNG is able to get a similar maximum ARI, but it's slightly faster than using Vamana or PyNN descent. We also have another experiment where we compared, we looked at the clustering quality relative to what exact DPC gave us instead of looking at the ARI relative to ground truth. So for this data set, HCNNG did not actually do better than the other 2 indices. So I think the takeaway here is that they all perform pretty similarly. Yeah, Lakshmi.
Did you compare the ARI for like the exact solution as well, or were the data sets like too large?
We did for ImageNet. I don't have that on the slide. Yeah, but we did, and so for ImageNet, like HCNNG, like they all perform pretty similarly. HCNNG was not like faster than the other 2.
Oh, so sorry, for the ARI, were these Approximate methods also kind of able to get this similar quality as the exact?
Oh, I think. Oh, let me see. Okay, I think this. Okay, this is a hidden slide. Yeah, so this shows you the ARI compared to the exact DPC. So yeah, we get pretty close. It's pretty close to 1. Yeah. Yeah, I was going to skip this slide, but since you asked, I'll show it to you. Okay. Yeah, so here we tested the scalability versus the number of cores that we use. So this is a 2-socket machine. It has 30 cores total, so each socket has 15 cores. And these speed-up lines are basically 1 for each data set. So when we use 1 complete NUMA node, 1 socket, the speed-up is pretty good. It's pretty close to 15. It's between 14 and 15. For some reason, like when we scale to 2 NUMA nodes, the speed up didn't increase by that much. It goes up to between 15 and 16. We didn't actually spend much time trying to optimize for the cross-socket performance. And as we'll see later, most of the running time actually was dominated by the graph index construction and the k-nearest neighbor, which we just used out of the box. But I think it would be interesting to investigate whether we can further boost the performance here. Okay, here we're looking at the scalability as we vary the data set size. So these are using the synthetic Gaussian data sets I talked about earlier, ranging from 10 to the 5 points to 10 to the 8 points. Each line corresponds to a data set with a different number of clusters. This is in log-log scale, clustering time versus data set size. And here we actually looked at the slope of the best fit line through these points, and we found that the slope was actually pretty reasonable between 1.1 and 1.2. So empirically, for this data set, it scales as a function of n to the 1.2, which is much better than theory. So in theory, the worst case performance is actually cubic due to the nearest neighbor graph construction time. Here we looked at the decomposition of running time across the different steps. So the blue bar corresponds to constructing the nearest neighbor index. Orange corresponds to computing the densities, which includes finding the k-nearest neighbors. Green corresponds to finding the dependent points. And then red corresponds to the last step of finding the clusters using a union find. So we see that most of the time is spent in constructing the index and in computing the densities. Computing the dependent points, it did take longer before, but because we used this doubling approach and did some optimization there, it got a lot faster. Yeah, Kuba?
So it seems that computing dependent points is a harder problem because this is like a filtered search problem as opposed to density, which is just a regular nearest neighbor search. Is it because, does it turn out like this because in many cases you can reuse the previous results to do the dependent
Yeah,
points?
I think that's the case. So for many of these points, they were able to find a dependent point within the k-nearest neighbors that they already found in the previous step, so then you didn't need to query
Paid
the
off
index.
by the previous, okay,
Yeah,
that makes
yeah.
sense.
Okay, we also compared to other implementations for spatial clustering. So FastDP is basically the state-of-the-art DPC algorithm for high-dimensional data. It's a sequential algorithm. K-means, it's a standard baseline clustering algorithm. We used a parallel implementation from FEISS, which we found to perform the best. And then we also looked at dbScan, which is another spatial clustering algorithm that's density-based. And we used the implementation from scikit-learn, which performed the best for high-dimensional data. Okay, so here are the results on two of the data sets, ImageNet and MNIST, both image embeddings. So PCAN is the blue line, K-means is in red, FastDP purple, and dbScan in blue. So again, we're plotting the Pareto frontier. So first of all, we see that PCAN and K-means are just better than FastDP and dbScan. And then between PCAN and K-means, sometimes PCAN is better, sometimes K-means is better. It really depends on the data set. So for ImageNet, PCAN is able to get higher quality clusters at a similar running time. And then for K-means, it was actually able to get higher ARI clusters and faster. Yeah.
How did you tune, for example, K-means? Did you just do some kind of grid search, or did you use the K that matches with the ground truth?
For k-means, I think we varied the k variable. I can't remember what other variables were tuned there. Yeah. Okay. Yeah, so in general, we found that k-means was faster for data sets with a smaller number of clusters, which makes sense because the running time of k-means is proportional to the number of clusters you have. And MNIST has 10 clusters, whereas ImageNet has 1,000 clusters. So k-means was better for MNIST, which makes sense, and then it was worse for ImageNet. However, what if we don't know the true number of clusters? So the results so far assume that we knew the exact number of clusters in our data set. So if we don't know the true number of clusters, DPC actually has an advantage. It's a hierarchical algorithm, so it actually outputs a dendrogram, which represents clusterings at different scales. So here, all of the leaves here correspond to data points, and then the dendrogram is a tree where if you just choose a horizontal line through this tree at any height and cut it there, the subtrees you get will correspond to some particular clustering. And using this approach, you can test clusterings with different numbers of clusters relatively quickly. Basically, if we want to cut the dendrogram at a different height, we just need to rerun the union find step, which was very fast, as we saw earlier. On the other hand, k-means requires you to rerun the entire algorithm from scratch every time, and that can be quite expensive if you want to explore different numbers of clusters. Okay, and then here we actually looked at what if you didn't pick the right number of clusters. So the x-axis is the ratio of the number of clusters you used in the algorithm to the number of clusters in the true answer, in the ground truth. And we see that if you pick too many clusters, the ARI of k-means actually drops pretty rapidly compared to pcan. So the orange line is k-means, blue is pcan. So we see that the accuracy of k-means is pretty sensitive to the number of clusters that you pick. Okay, so let me conclude now. So we designed the pcan framework for density peaks clustering. It supports many different DPC variants, and we also introduced this doubling method for finding approximate nearest neighbors with higher density. And then we found that we get significant improvements in running time and clustering quality over FastDP, which is state of the art for high-dimensional DPC, as well as dbScan. And then it's competitive with k-means. So sometimes it's faster and sometimes it's slower, but it has this nice advantage of being a hierarchical algorithm compared to k-means. All right, so that's it. Thanks.
Time for a couple questions.
So in the cases where the k-means was approximate, it looked like there were good empirical guarantees that the ARI was good, but are there any theoretical guarantees as to how good the approximation
Oh, for
ratio is?
DPC or?
Yeah.
Yeah, no, we don't have any theoretical guarantees for this. We thought about it for a while, but we weren't able to show anything in terms of like approximation to the ARI, unfortunately. But that's an open question.
I guess I was wondering on these data sets, it feels like you mentioned that a lot of times you can find your parent locally, but sort of further and further away, there seems to be a diminishing value to that, right? But basically, like if you're the root of some smaller subtree, is that in some sense enough, and you don't really need to go to the build the full tree? Like the last few.
Yeah, that's a good question. Let me actually go back to this slide. So basically, like most of the points are gonna find a dependent point in the the first round, basically. Yeah. Some of the points, like basically, if they have pretty high density and their dependent point is very far away, you're not gonna find that even if you keep going for many rounds. So like in practice, we found that after most of the points already found a dependent point, the remaining points, they're unlikely to find a dependent point unless you look at all of the points anyway. So we just switched to a brute force search. Yeah.
And so how soon does that tend to cut out?
I think in our experiments, when there are about 300 points left, we just switched to the brute force thing.
And how many doubling rounds have you done at that stage?
I think it depends on the data set. So we start at K, and then I don't remember exactly. It's probably around 10 and 20, something like that. Yeah.
All right, let's thank Julian again. Make sure you take your microphone on.